Here's what's from the IB syllabus in terms of waves that they'd like you to know. You should be able to describe a wave pulse in a continuous wave, what's sometimes also known as a traveling wave. You should state that traveling waves or progressive waves transfer energy. We'll talk about that. Describe and give examples of transverse and longitudinal waves. We'll explain that today. There's also a third one in here, which is not in the syllabus, which is called a surface wave, which we'll also discuss. Describe the terms crest, trough, compression, rarefaction, vocab terms right there, and another list of vocab terms. Define displacement, amplitude, frequency, period, wavelength, wave speed, and intensity. You've already been introduced somewhat to the idea of frequency and period with simple harmonic motion. We'll talk about it more specifically, and displacement and amplitude for that matter. We'll talk about it more specifically with waves and traveling waves as opposed to simple harmonic motion. Derive and apply the relationship between wave speed, wavelength, and frequency. So that's kind of our goals. Those are the goals for today. Relatively straightforward stuff. Let's start with the idea of energy, okay? With particles, that's one way to transfer energy. And last semester we talked a lot about mechanical energy, specifically kinetic energy and potential energy, right? And doing work, transferring energy from one object to another. Remember, work is the process of transferring energy from one place or from one object to another. Now, if I'm thinking in the world of particles and I want to transfer energy, there has to be an exchange of material. There has to be some sort of an exchange of stuff, right? If I'm really mad at Taylor and I want to smack her upside the head, I have to walk over and actually hit her, right? To give her that energy, there has to be physical contact. I can't just sit here and like try to hit her and it'll work, right? I'm not a Jedi Knight yet, so I can't do that stuff. Okay? But, exactly, someday. But with waves, the cool thing with waves is I can transfer energy through waves without actually transferring material from point A to point B. I can give Taylor energy through waves without actually making contact with her. Classic example is a sound wave. Think about this for a second. Right now you're hearing my voice, except for Luke. Okay? I'm creating sound waves in my vocal cords that are coming out of my mouth, and they're going into your ear. The energy is going from my mouth to your ear, and you can hear it, but there's no stuff going from my mouth to your ear. I don't have to have atoms travel across the room and into your ear. Instead, it's this wave disturbance. It's the energy traveling in the form of waves that dissipates out and gives the energy to your eardrums, okay? Light's the same way. Light is traveling from the sun to the earth, and there is stuff coming from the sun to the earth, but not, okay, bad example. The light itself is traveling in the form of a wave. It's not like there's material that's transmitting that stuff to us, but we'll get into, except for what Isabel mentioned earlier, but forget about that for a second. Right now, just think about waves can transfer energy without there being a net transfer of material, okay? It's one of the cool things about them. Sam?
About like a shock wave.
What about it? So let's see if we can define what a wave is then. Here's kind of a good definition. A rhythmic disturbance that carries energy through matter or space without net displacement of the medium. All right, that's kind of what I'm trying to explain to you. So a wave is a disturbance. It's specifically a rhythmic disturbance that transfers energy without actually transferring the material from point A to point B, or the medium from point A to point B. The medium does move, okay? It does vibrate, it does oscillate, it does simple harmonic motion, but there isn't net displacement from point A to point B when a wave passes through. Does the sound wave what? Yes, anything that's going to have some sort of friction will have damping taking place. Yeah, but even so, that's one of the reasons why at some distance sound will get weaker and weaker and weaker and dissipate, and you won't hear it anymore. Okay? So again, we've already talked about we talked about sound waves. What are some other types of waves you can think of? Okay. Water waves, excellent. Microwaves, which is like the whole electromagnetic spectrum. So X-rays, microwaves, radio waves, visible light, gamma rays, ultraviolet, infrared, radio. Excellent. Okay. Now here's a weird thing. You guys ever heard of cosmic rays? Okay. Those aren't waves. Okay. Those are particles. Weird. We call them cosmic rays, but they're actually little particles, little helium nuclei and hydrogen nuclei flying at real high speeds. No. Excellent. We'll talk about the difference between a mechanical wave and an electromagnetic wave. That's one of the fundamental differences. Certain waves require material, require a medium. A sound wave is one of those. No. Except for in the movies, but not in reality. You can't talk in space. So those are all great examples of waves. So we talked about water waves, sound waves, electromagnetic waves. Microwaves are a type of electromagnetic wave. And also there's earthquake waves are another good classic example. When an earthquake happens, there's actual waves traveling through the ground, and they do longitudinal, transverse, and surface waves. So earthquake. But the most fun waves of all, there you go. Okay, there's a classic wave. Okay, that's a water wave. This is a fun activity on a water wave. If you've ever had the opportunity to go surfing, one of the cool things about surfing, there's a lot of great things about surfing, but if you ever actually catch a wave and catch it well and catch it right, and you're on the green water in front of the white water and all that stuff, one of the things that's so amazing about surfing is you are riding energy. That's it. You are riding a wave of energy, and it's such an incredible feeling to do that it's just kind of neat. Okay, anyway. So let's differentiate. That was not me. No. Soul surfers. All right. Okay, so let's differentiate, and Robbie, this comes, I think, from a question you asked earlier. Differentiate between the idea of a mechanical wave and electromagnetic wave. Mechanical waves are waves that require a medium to travel through, okay? And sound is a classic example of a mechanical wave. It needs material in order for it to propagate itself. When you have a mechanical wave, the speed of that wave, how fast that disturbance travels through the medium, is determined by the medium through which it is traveling. The material, yep. No, sound needs a material to travel through.
So like air.
Like air, okay. And it travels at different speeds depending on the material it's traveling through. So sound travels faster through water than it does through air, okay, for example. It does. All right. Okay, electromagnetic waves, you guys, one of the things that distinguishes electromagnetic waves is that they do not require a medium. They can travel through empty space or a vacuum. Sometimes. Some waves and some medium. Now let's talk about the electromagnetic spectrum. Hopefully you guys are somewhat aware of this, but there is this grand spectrum that runs from very big waves to very small waves. Very nice. Okay, and somewhere in this we have visible light, the stuff that we see. And visible light is a type of electromagnetic wave, and it's one little piece of this grand spectrum. These are long, and these are going to be short. So let's give me some names of some of these electromagnetic waves. Microwaves are somewhere right in here. Someone said X-rays. We'll put those right over here.
Is it a gamma ray?
Someone said gamma. What else? Radio. Stingray. What else? CAT scan, I think, is something different. Ultraviolet, UV, infrared. Blu-ray actually fits in here, you guys. Remember, visible light is red, orange, yellow, green, Blu-ray, indigo, and violet.
Violet ray would be better.
Yes, ultraviolet would be even better yet. X-ray would be even better yet. Okay. Ray Charles. Couple of things about this spectrum. Hold on a second, while I'm on the electromagnetic spectrum. All of these waves are the same type of wave. They are all electromagnetic waves. They are oscillations in the electric and magnetic field. They all travel at the same speed, which is speed of light, 3 times 10 to the 8th meters per second, 186,000 miles per second. That's in a vacuum. In a vacuum, when there is no medium, they all will travel with the same speed. Please recognize that radio waves are not sound waves. Don't get those confused. Radio waves are electromagnetic waves. Sound waves are mechanical waves, okay? Even though we transmit sound using radio waves to a thing called a radio, which then makes sound, the radio waves themselves are not sound waves. You've got radio waves passing through this room right now, and you cannot hear them, unless you pick them up with a receiver, okay? Now, we talk about the speed of electromagnetic waves being the speed of light, which is 186,000 miles a second, or 3 times 10 to the 8th meters per second, which is 7.5 times around the Earth every second, okay? So it's really fast. That's in a vacuum. One thing you should also recognize is that when electromagnetic waves go through other materials, like air or water or glass or diamonds or crystals or whatever, the speed changes. They actually travel more slowly through those mediums. So the speed of light is slower through glass or through water or through air than it is in a vacuum, okay? We've talked about specific types of waves, sound and electromagnetic spectrum and earthquake waves and water waves, but really there are 3 main categories of waves. Well, okay. There's mechanical and electromagnetic. That's kind of one way to group them. Mechanical requiring material, electromagnetic not requiring material. Well, those are 2 categories real roughly, but these are let me just show you what I'm talking about here, okay? There's transverse waves, okay? In a transverse wave, the medium is moving perpendicular. It's vibrating or oscillating perpendicular to the direction of the wave travel, or perpendicular to the direction that the energy is actually traveling. Transverse waves are not able to travel through a fluid. Let me demonstrate what I'm talking about. So why can a transverse wave, now both of these are types of mechanical waves. Recognize that electromagnetic waves, light, those are transverse waves, and they can travel through a fluid because they don't require a medium. They're not dependent upon the medium to continue traveling. But a mechanical wave can't travel through a fluid because a mechanical transverse wave, I mean. Here's the transverse wave, woohoo, okay? And it's traveling this way. Now recognize if I look at one little piece of the material, let's say it's a slinky, okay? This little piece is vibrating up and down in simple harmonic motion. When it gets displaced from equilibrium, what is it that brings it back to equilibrium? What is it that's pulling it back to equilibrium? But what's exerting those forces? Think about the slinky. If I send one down the slinky and the slinky gets displaced, why does the slinky come back? What? Yeah, it's connected to the molecules around it, and those molecular connections are trying to bring it back to equilibrium, right? But in a fluid, in something that looks like a liquid, those molecules aren't so tightly connected. So as soon as I displace it off to the side, all the molecules around it aren't trying to snap it back to equilibrium. It just flows, right? And so the energy doesn't go anywhere. You displace the medium, and it never rebounds back. We'll get there. That's on the surface, though. In the water, there will be no transverse waves traveling, okay? And this is one of the ways we know this interior structure of the Earth, okay? Because earthquake waves are both transverse and longitudinal. Longitudinal being the second type of mechanical wave, okay, where the medium is oscillating parallel to the direction of motion. And those can travel through a fluid because you're going to have this compression and then kind of a rebound from the compression. Sound waves are longitudinal. Excellent. Electromagnetic waves are transverse. With the Earth, when we have an earthquake, let's say we have an earthquake right here, big earthquake and everything's shaking, you get both kinds of waves, transverse and longitudinal. Now those waves travel out through the Earth, and you can detect them. If you have very sensitive detectors, you can detect them all over the place. So this is kind of a cool thing. This is one of the ways geologists have studied the interior of the Earth, because if I have a detector here, it only receives longitudinal waves. So what do I know about between here and here, what must exist? There must be a fluid in there. There must be some liquid in there. And then I go over to this receiver, and it only receives longitudinal waves, so I know that it's traveled through a fluid as well. But this receiver has received both transverse and longitudinal. So it's only traveled through a solid. So as the more detectors you can do that, you can actually start to map out these layers of the Earth that are liquid and solid. And that's how geologists have studied, knowing that we have a liquid mantle and all this other stuff deep down in there, core, solid core, liquid core, things like that. Okay. The third type of wave is known as a surface wave. And Ellie, this is what you were asking about, I think, on the surface of the water. Okay. These will travel along the surface of a medium, and they actually have characteristics of both longitudinal transverse. Instead of either being perpendicular or parallel, you get a little bit of both, and actually you end up with circular motion on the surface. So out in the deep ocean where you have waves rolling by, if you put something floating on that and watch it, it doesn't go up or down or back and forth. It actually goes in circles. As the waves pass through, it does circular motion. Okay. And earthquake waves also create surface waves, and these are the ones that are the craziest. When you're in an earthquake, have you ever been in a big earthquake? All right, so here's our diagram. What type of wave is this top one? Transverse. Bottom one? Longitudinal. Again, our definition is that in a transverse wave, the medium is oscillating perpendicular to the direction that the energy is flowing, okay, or that the wave is actually traveling. If I looked at an individual molecule, it would be vibrating perpendicular, whereas in a longitudinal wave, an individual molecule is vibrating parallel to the direction of energy travel. What happens with longitudinal waves is you get these areas where the medium is all scrunched up or compressed, and you get other areas where the medium is all stretched out. And another word for being all stretched out is rarefaction. Rarefaction. Okay, sound waves are longitudinal waves in the air. So the air molecules are vibrating back and forth when sound travels through them, and you get these areas of high pressure and low pressure. And then you put your ear up to, when that sound wave reaches your eardrum then starts to vibrate back and forth as well when the different pressures hit your eardrum, and you sense that as sound. All right, let's check out these websites, see if we can get a good visual on transverse and longitudinal waves. Okay. This is kind of like a slinky, but now we can actually observe it a little bit more closely. What kind of wave? Give me an example of one. Slinky wave or electromagnetic waves. These are electromagnetic waves or transverse waves. Now notice that if you look at an individual molecule or an individual piece of the slinky, it's vibrating perpendicular to the direction of the energy motion. That's the definition of a transverse wave. If I change the wavelength, it's still doing the same thing, okay? It's not going anywhere. It is moving, but it's not actually going anywhere. It's just doing simple harmonic motion. Each molecule is doing simple harmonic motion, okay? It's not going anywhere. It's back where it's... Now here are examples of longitudinal waves. Notice that in a longitudinal wave that the material is vibrating or it's oscillating in the direction of energy travel. And again, an individual part of the medium doesn't actually have any net displacement. It's just moving back and forth, but in the same direction that the energy is traveling, okay? It is also simple harmonic motion. And notice that you get these areas where the material is compressed, and you get these areas where the material is more spread out or rarefied, and that is how the energy...
Some materials like walls get compressed. Like that's something I don't understand.
Okay.
Like Mark, like your medium is...
Notice now with this little graph I turned on, if I look at one of the molecules of the medium and graph its displacement versus time, suddenly I get that transverse wave. I get simple harmonic motion again, sine wave, cosine wave, all that stuff. It's all connected. Same thing here. This upper picture would be a picture of like sound waves traveling through the air. Each little dot would be an example of a molecule. Notice that each molecule would be vibrating back and forth this way, and you get these regions of high pressure and regions of low pressure that would be traveling through the air or through the medium, and that's what we would experience as sound wave. If I was to graph the pressure versus displacement, it would be a nice sine wave. This whole wave function kind of just keeps coming back at us over and over and over. Oh, look, simple harmonic motion. Yeah, all over again. Okay. Look at that, slinky. Now, something to be thinking about, there's a lot of questions about this to make sure you're understanding kind of the mechanics of wave motion. Here's a transverse wave pulse. Notice that right here, if I look at a piece of the string, it's moving in the upward direction. Right here, if I look at a piece of the string, it's moving in the downward direction as this pulse moves from left to right. Can you kind of visualize how that works from what we've seen so far? Okay. All right, we've talked about this. Let's just get to some vocab now. What are some words you know associated with waves? Trough. Crest. What's that? Frequency. Amplitude. Wavelength. And what's that one that's associated with frequency? Period. Okay, good. Medium too. Here are the four main ones you really need to know. Wavelength, amplitude, period, and frequency. These are physical properties of waves that we use to describe them. Wavelength in your equation is going to be represented by the Greek letter lambda. Lambda, okay, like the tri-lambs. You guys seen Revenge of the Nerds? Awesome, okay, lambda, lambda, lambdas. All right, we measure wavelength in meters. It is a measurement of a distance, a specific distance on a wave, okay. Amplitude we've talked about is represented by x sub 0 or x naught, and it is also measured in meters because it is a distance. It's how far something is displaced from equilibrium. Period is represented by the capital letter T because it is a time frame, and it's a special time frame. That's why it gets the capital letter, and it is measured in seconds. And frequency will be represented in your equations by the lowercase f, which, hey, that one actually makes sense. And it is measured in a unit called a hertz, and a hertz is a per second, okay? So a wave with a frequency of 60 hertz means it's vibrating 60 times each second. Sam? All right, so let's look at specifics here of these definitions. Here's a picture. Here's a picture of them. Wavelength is, it can be the distance from one crest to the next. No, because period is a measurement of time. Wavelength is a measurement of distance. Okay? Yep, okay. But we always talk about wavelength being from crest to crest or from trough to trough, but it doesn't have to be. It just has to be the distance from one point on a wave to the same point on the next wave. Okay, so I could just as easily say from here to here is my wavelength. All right. This is the trough here. This is the crest. Okay. The amplitude is the measurement from equilibrium to either the crest or the trough or to maximum displacement. Please don't confuse amplitude as being this distance. Okay, from crest to trough, that's actually twice the amplitude. Okay, because amplitude is measured from equilibrium.
Is there ever a time when the amplitude is different on top and bottom?
Not if we're talking about simple harmonic motion, and generally in this class we'll try to keep it simple. In reality, yes, that will be the case. But the period, so Ellie, you brought this up. This looks very similar to the period, but the period is a measurement of time. The time it takes to do that one complete wave motion, and the frequency is the number of wave motions that happen every second. So I think I actually have all this stuff written down. There we go. Wavelength, the shortest distance between the same point, the same 2 points on a continuous wave. That could be crest to crest, it could be trough to trough, it could be anywhere. It's measured in meters or some fraction thereof or some metric multiplier thereof. All right, so our definition of amplitude is the maximum displacement from equilibrium position. Please remember that in waves, the intensity of the wave, which has something to do with the amount of energy it has, is proportional to the amplitude squared. Intensity, okay? It's kind of it's basically the energy that a wave carries, except for electromagnetic waves. For mechanical waves, the intensity is proportional to the square of the amplitude. The period of a wave is the time it takes for a wave motion to repeat itself once. And it will be equal to the period of the thing that created the wave, or the source of the wave. So again, period is a measurement of time. Okay. Frequency. Yeah, frequency measured in hertz. It is the number of wave cycles that happen every second. Okay, the number of wave cycles that happen every second. And classic examples where you come into contact with frequency on a regular basis is radio stations. And I believe I talked about this before, but on the FM dial, you listen to stereo on the FM dial, the number of your radio station, okay, 103.1, in megahertz. Okay, you're tuning into that electromagnetic wave, that radio wave that's vibrating with a frequency of 103.1 million hertz. If you're more of an AM kind of guy, it's not the amplitude, it's how fast it's vibrating. It's okay. They don't sound at all because they're radio waves. They're electromagnetic waves. Okay. Excellent. If you're listening to the AM dial, you're talking about kilohertz. Okay. The radio station on the AM dial is thousands of hertz or thousands of cycles per second. Those radio waves that are transmitting that energy. And let's see. Finally, the relationship between period and frequency is inverse. Frequency is 1 over period. Period is 1 over frequency. This will come into play quite frequently. Frequently when we talk about it. Okay. So waves. The frequency of the wave is determined by the thing creating the wave. Okay. How many waves you get per second is determined by the source, not the material through which it travels. Okay? If I have a wave of 100 hertz, 100 cycles per second, and it goes into a new material, it's going to go into that new material at 100 cycles per second. That frequency will stay the same. The wavelength, however, will change. Okay? And we'll talk about that and get into the calculations of all that. But just kind of remember that frequency is one of the things that stays constant. The speed and the wavelength are the things that change when a wave enters a new material. So let's talk about speeds of a wave. Velocity. Okay. Traditionally, we've talked about velocity, distance divided by time, right? Remember that? It was like our first equation ever way back in September last year, okay? Distance divided by time. That makes sense, right? Meters per second, miles per hour. Great. Well, with a wave, it's the same idea, okay? The same ideas. And there's a lot of different motion going on in a wave. So let me draw a quick transverse wave here. If I was talking about the velocity of the medium, or a piece of the medium, it would be simple harmonic motion, right? Sometimes that little particle would not be moving, and sometimes it would be moving at maximum when it crosses equilibrium, and it would create a sine wave and everything we've just talked about. But the wave itself, if I'm curious about how fast the wave disturbance is moving, that's a different concept, and that will be a nice constant speed for a given material. And it will be the same thing. It'll be distance divided by time, but in wave terms, we don't say distance and we don't say time. What do we say? We say wavelength for distance, and we say period for time. Okay? Excellent. All right? So there's our wave velocity equation. The velocity of a wave is equal to wavelength divided by period, or wavelength times frequency, since period and frequency are inversely proportional. The speed with which a disturbance travels, the speed that a wave travels, is determined by the medium. The medium dictates how fast it goes and pretty much nothing else. And if you think about a mechanical wave, let's think about, you started off talking about why does sound travel faster in water or faster in some materials than another. Well, let's think about it for a second. If I have a sound wave and it's traveling, remember that the molecules, imagine these being molecules of the medium, are vibrating back and forth. What determines how fast my disturbance will move is how quickly the molecules snap back to equilibrium position, right? You with me? So in a material like a metal, but it's a solid, those atoms, they don't want to be disturbed. They don't want to be away from equilibrium because they're really tightly bound, so they snap back really quickly. Therefore, the disturbance travels really fast. Something like air, it's a little bit more loosey-goosey, then it travels more slowly, right? So that's one of the factors. Okay, here's where we started. Huh. Did we do it? Did we do it? Let's see if we did it. Can you describe a wave pulse? You bet you can. Pow. Yeah. Okay. Could you state that waves transfer energy? Certainly. Can you give example of transverse and longitudinal waves? Right on. Okay. Look at these terms. Crest, trough, compression, rarefaction. We got those covered. Okay. Displacement, amplitude, frequency, period, wavelength, wave speed, intensity. Okay. And then wave speed, wavelength, and frequency. Awesome. Bless you.